All right, the plan for today is to finish up Taylor and Maclaurin series, uh, and also to note that sample Unit 3 exam is available now on WebAssign. I'm also going to just post a review of series overall with some practice problems and solutions. So if you want to go back through and just kind of review the chapter as a whole, that'll be available. So the Unit 3 exam is, or sorry, um, the sample Unit 3 exam is available this week. I think I might have said that wrong. Sorry, I have a little bit of brain fog today. My allergies are really going crazy. But the sample Unit 3 exam is available this week. It's up now on WebAssign. Unit 3 exam will be available next week. And we're going to wrap up Terrell and Maclaurin series and general series today. So that's the plan. Then for next week, we're going to start into chapter 12 for our last few class meetings with an optional review session, or basically office hours, on Wednesday the 8th from 1 to 3. And the final exam will be available Friday the 3rd through Friday the 10th. So I've already made the examity sessions available, so you can go on, you can set up your time, you can get all of that set up ahead of time if you want. But the final exam will be just like our previous exams, taken on WebAssign through Examity. The sample exam is already posted, it's already available. You can use a formula sheet, either one that you made yourself or one that you downloaded or typed up or whatever. So you can use a formula sheet on the final exam, just like the Unit 3 exam. You can use a formula sheet there as well. So the quote of the day today is more geared toward my stats class, where we're talking about correlation and regression, but the quote of the day is to be cognizant of assumptions. In a crash, like a stock market crash, correlations go to 1. So what's the basic idea here? You might have heard the saying, like, don't put all your eggs in one basket, or when you're investing in the financial markets, you don't want to put all your money in one stock. You want to diversify among a bunch of stocks to try to reduce risk. And basically the argument from that is it's a really elegant mathematical model, sometimes called modern portfolio theory or Markowitz portfolio theory. And essentially what it shows is that you can reduce your risk by buying a bunch of different assets, because the assets tend to be less heavily correlated the more you buy. In other words, if you own 100 stocks, if one stock has a really good day and another stock has a really bad day, they kind of even out. But if you had only bought one stock, you might have bought the stock that had a really good day and you'd be really happy, but you might have also bought the stock that happens to have a really bad day and you take a big loss. So it's important to note, though, that there is an assumption here. If you went to a financial advisor and said, why should I diversify? They probably first say, like, well, don't put all your eggs in one basket. And if you push them and said, well, what's the actual financial argument? What's the math? What's the finance support behind it? They would probably bring up what I just brought up. And there's an important point, though, is that an assumption of Markowitz portfolio theory is that the correlations, the way that the stock movements relate to one another, are constant over time. But in reality, they're not. When the market is doing well or kind of flat, the stocks associate with one another a certain way. Maybe, when these types of stocks tend to be high, these other types of stocks tend to be low, and vice versa, maybe something like that. So they kind of offset one another. But in a crash, when the market crashes, which, depending on who you listen to, might be coming up pretty soon here, but people have also been saying that the market was going to crash for the last 3 years or so. So who knows? In a crash, pretty much all stocks go down. So all of a sudden that they all start to behave the same when the market's crashing. And that assumption of modern portfolio theory isn't satisfied very well. So you pay the idea of diversifying is to sacrifice the upside in order to not suffer such a bad downside, but you really end up sacrificing more on the upside than you get protection on the downside. So that's a very real cost to diversifying. And but I think it also it should be said that doesn't mean you shouldn't diversify. There's also a benefit. It's a little bit like buying an insurance policy, right? You're on average paying a bit more than you otherwise would, but the benefit you get is the more consistent returns. Okay, so that's the idea for today. And just as a, I mean, this obviously applies in many more places than this, especially when we're going through our series tests. We don't want to apply the result of a theorem, the result of a series test, if we haven't checked the assumption. So some of them have an assumption like the terms of the series are positive and decreasing. Some of them are I just lost my train of thought. Some of them, like the alternating series test or the alternating series estimation theorem, only apply to alternating series. So we don't want to mistakenly apply those to those ideas to a series that's not an alternating series, right? So we want to make sure to always check our assumptions of any theorem before applying the results. All right. So moving on then to the next example in Maclaurin series. Before we move on, are there any questions on Taylor series, Maclaurin series, anything about exam 3 or the final? Okay. So moving on to Maclaurin series, we have a couple more examples. For this one, we want to use Maclaurin series to demonstrate Euler's identity, e to the I theta equals cos theta plus I sine theta. Exponentials that have imaginary numbers associated with them, we often see those in places like maybe differential equations or in physics, and these like have the feel of oscillations, like imaginary eigenvalues, so to speak, have the feel of causing some kind of oscillatory phenomenon. And this is really the mechanism through which I think that can most easily be seen. So let's try to show this identity. Again, we haven't really worked with imaginary numbers much. So this is a little bit outside of the kind of typical assumptions of the course. We're dealing with imaginary numbers here, not sticking to real numbers. So what do we need to know about imaginary numbers? Well, really all that we need to know is, number one, that things like derivatives and so on work essentially the same in the complex world as in the real world. So if I'm like differentiating something with an I in it, the I just acts like a constant essentially. And also that I squared equals -1. Therefore, I cubed equals -I. I to the 4th equals 1. And I to the 5th equals I. And then I to the 6th is the same as I squared, or -1. We notice that we're trying to link E, cosine, and sine, and I actually look at the power series representations for e to the x sine x and cos x, and if I blur my eyes a little bit, it kind of looks like sine x plus cos x makes e to the x. I have my odd powers, x to the 2n plus 1 over 2n plus 1 factorial, and my even powers, x to the 2n over 2n factorial. It seems like if I add my odds and my evens together, if it wasn't for these -1s, then I would get e to the x. I would just get all of the x to the n over n factorials, odd and even, combined together. Note that the radius of convergence for all these is infinity, so I can be a little bit maybe almost flippant about what algebraic structures I'm applying here. I don't have to be nearly as careful. These will converge absolutely on the whole real line. So none of this craziness will happen that we've seen in some of the other situations where we have conditionally convergent series or even divergent series and we're trying to manipulate them. Everything converges super nicely here. So we can be a little bit more relaxed about what algebraic tools we use. So let's start with the right-hand side. If we're trying to show an identity, it usually is easier to start with the more complicated side. So cosine theta plus I sine theta. And I can see that this is going to be cosine of theta gives me sum minus 1 to the n, x to the 2n over 2n factorial, plus I times sine theta. Gives me that. And this messy looking thing here is an I. Didn't write that very well. There we go. And I want to make this look like e to the I theta, which is going to be sum n equals 0 to infinity of, well, e to the x would be x to the n. So this is I theta to the n over n factorial. I could also go the other way. I think it might even be easier to go the other direction, but going this direction, we can also get a little practice working with indices and so on. So this is my goal, to get to something like this. I see that I have even powers and odd powers. Maybe I'll choose to rewrite this as some n equals 0 to infinity even x to the 2n over 2n, or sorry, x to the n over n factorial. So this is like n equals 0, n equals 2, n equals 4, and so on. And then what do I have? I have minus 1 to the n over 2, I suppose. So n equals 0, n over 2 is 0. And that gives me minus 1 to the 0. When n equals 2, n over 2 is 1. And I get minus 1 to the 1. So that looks good. Plus I sum n equals 0 to infinity, summing over the odd numbers. And this will give me x to the n over n factorial. So I'm getting closer. And then minus 1 to the n. I didn't leave myself quite enough room here. So this is going to be times minus 1. And when n equals 0, down here, I want that to correspond to n equals, or sorry, when n equals 1 down here, I want that to correspond to n equals 0 up here. So I need n minus 1 over 2. And then when n equals 3 down here for the next odd number, I want that to correspond to n equals 1 up above. So 3 minus 1 is 2 over 2 is 1, and that does seem like it works out. So now what do we have? Sum n equals 0 to infinity even x to the n over n factorial minus 1 to the n over 2 plus, now we're going to bring this I inside. Sum n equals 0 to infinity odd. If I can write odd. There we go. X to the n over n factorial. And bringing the I inside, I get I times minus 1 to the n minus 1 all over 2. All right, so now I need to somehow make all of this look like I theta to the n in both of these series, or I x to the n. we'll say theta equals x up here because I switched my variable when I was looking back at these series. Sorry, like I said, I have a major case of brain fog today. All right, so what do I need to do here? I need to incorporate this -1 to the power in with the x to the n. So summing over the evens. And I want something x to the n power. So what do I need? If I have -1 to the 1/2 times x to the n power. I'm not doing a good job with my spacing today. So I have my x to the n already, and I want to move this -1 to the n over 2 inside of that power in that same base. So I need a -1. If I have a -1 here times x to the n, this gives me -1 to the n. So I need a 1/2 power inside of here as well, over n factorial. This is going to be sum n equals 0 to infinity over the evens. And -1 to the 1/2, the square root of -1 is I times x to the n over n factorial, summing over the evens. So this is the even bits that I want. This is the even part of that function. And then I want to do a similar thing with the odds. So I have x to the n over n factorial, but summing over only the odds. So when n is an odd number, I have my something times x to the n power over n factorial. What do I have here? Well, I is the square root of -1. Let me pull these off to the side. I times -1 to the n -1 over 2. But I is the square root of -1, or it's -1 to the 1/2 times -1 to the n -1 over 2. Or this is -1 to the 1/2 plus n -1 over 2, or that's plus n over 2 minus 1/2, and these bits go away. So this is also -1 to the n over 2. So again, if I put a -1 inside of here, I get a -1 to the n, and I need a 1/2 there. And here I get ix to the n over n factorial. But I have the same thing that I'm summing. I'm summing over the evens and over the odds and adding them together. So this is sum n equals 0 to infinity of all n's. Ix to the n over n factorial, or that is e to the ix. If you want to do an example of practice, you could try doing it the other direction and see how everything breaks apart. I think the strategy is maybe a little bit easier the other direction, or the details are a little easier. But at this point, we've essentially proved Euler's identity. I mean, we didn't really prove that all of these ideas work in the complex world, like that we can, move the I inside of here or any of that, but There are a couple details we glossed over, but I would say that um, this is pretty good evidence, right? It's not, there might be a couple little details we have to clean up. Because again, all of the calculus we've developed really only applied to real numbers. We haven't thought about how it might apply to complex numbers, but it does apply just as well to complex numbers. Okay, so let's look at the next example. Find the Maclaurin series representation for f of x equals x over 1 minus x squared. So we want a power series representation centered at 0 for this. I suppose I could start taking derivatives, but this looks like a pretty nasty function to take a whole bunch of derivatives of. But it turns out that if I find a convergent series representation for the function, it's going to, at 0, it's going to be in the Maclaurin series. So what do I want? I want to find a power series representation centered at 0 that is equal to this function. And what's my goal? My goal is to find the CNs. I want a formula for my CNs. I know that these two things are equal to one another, or in other words, C naught plus C1x, and so on, equals x over 1 minus x squared. Let's assume we're working on our interval of convergence. Then what we can actually do is we can multiply through by 1 minus x squared. And then all that stuff on the left-hand side should just turn out to be x, or in other words, should turn out to be 0 for the constant, plus 1x, plus 0x squared, plus 0x cubed, and so on. So my coefficient of x on the left side should be 1, and all the other coefficients should be 0. Okay, so on the left side, let's start multiplying this out and seeing what our different terms are. How can I get a constant? The only way I can get a constant is when the 1 hits the C naught. So C naught is my constant term on the left. How can I get a linear? C naught against x, or against minus x, or 1 against C1x. So my linear coefficient is going to be what? C1 minus C naught. And that's going to be times x. What is my quadratic coefficient? Well, I could get C naught times x times minus x squared, C1x times minus x, or C2x squared times 1. So this is going to be C2 x squared times 1 minus C1 x squared, and then minus C naught. And let's go maybe one, and this is going to be x squared. Let's go one more. For the cubic term, what is that going to come from? Well, I could have my C3x cubed times 1. I could have my C2x squared times minus x, so that's minus C2. Or my C1x times minus x squared, that's minus C1 x cubed. And I might actually see my pattern now that my coefficient of x to the n is going to be Cn minus Cn minus 1 minus Cn minus 2. And now what do I see? I see that my, so this all has to equal 0 plus 1x plus 0x squared plus 0x cubed plus 0x to the n, and so on. So these two sides have to be equal. And I see that my constant, C naught, on the left has to equal my constant on the right, which is just 0. I see that my linear term has a coefficient of C1 minus C naught on the left and a coefficient of 1 on the right. So C1 equals 1 plus C naught, or just 1. And then I see that for n bigger than or equal to 2, what do I have? Cn minus Cn minus 1 minus Cn minus 2. All of these other coefficients on the right are 0. Or Cn equals Cn minus 1 plus Cn minus 2. I have a recursion for n bigger than or equal to 2. So what's C2? C2 is C1 plus C naught. 1 plus 0 is 1. And then C3 is C2 plus C1, or 2. Or actually, Cn equals Fn, the nth Fibonacci number. So it turns out that my Maclaurin series coefficients are the Fibonacci numbers for n bigger or equal to 1, and the constant term is 0. So that's kind of interesting, right? I know these coefficients also correspond to derivatives of the function at 0. So differentiating this function and plugging in 0 will yield different Fibonacci numbers. So kind of an interesting relationship. And we got it again through kind of an ad hoc method. We have our kind of standard Maclaurin series, Taylor series construction method, taking derivatives, plugging in the center. But we also have seen several ad hoc methods, ways that kind of, if we see a certain problem and taking the derivatives are annoying, or maybe if we just want another way to solve the problem. Sometimes we have other ways to get the series representations that are non-standard. Okay, then let's look at this example. So find the third degree Taylor polynomial for f of x equals x to the 2/3 with center a equals 1. Let me make this window a little wider. Here. And then once we found that approximation, right, the third degree Taylor polynomial is a partial sum. It's going to be an approximation. Let's use Taylor's inequality to estimate the accuracy of the approximation on the interval 0.9 to 1.1. So going 0.1 units in either direction from our center. And recall the theorem, Taylor's inequality said that the absolute value of the remainder, or the absolute value of the error in approximating the function by the nth partial sum of the Taylor series is less than or equal to this, which more or less looks like the first term we leave off. X minus a to the n plus 1 over n plus 1 factorial. We see that in our first term we leave off. Now, of course, this x minus a is in absolute values because we took absolute values there. And the m, this constant m up here, I can't really select it, but it is the upper bound for the n plus first derivative over the interval of interest. Okay, so let's first work on finding the Taylor series. So I know if I want the third degree Taylor polynomial, I need up to the third derivative for that. And then I need one more derivative for my Taylor's inequality. So I need the fourth derivative. So the negative 1/3 comes down, leaving me with negative 2 over 9, x to the minus 4/3. The third derivative of minus 4/3 comes down, leaving me with negative 8 over 27, x to the minus 7/3. And the fourth positive 8 over 27. And the fourth derivative, the negative 7/3 comes down, leaving me with negative 56 over 81, x to the negative 10/3. For my partial sum of my Taylor series, I also need the center is 1, so I need f of 1 through f triple prime of 1. F of 1 is 1. F prime of 1, 2/3. F double prime of 1 is negative 2 over 9. And f triple prime of 1 is plus 8 over 27. Now T3 of x, the third partial sum of the Taylor series. Just a reminder, T3 of x is going to be f at a plus f prime at a, x minus a to the first, plus f double prime at a over 2 factorial, x minus a squared, plus f triple prime at a over 3 factorial, x minus a cubed. Or it's going to be f of 1, or just 1, plus f prime of a, 2/3, times x minus 1, plus f double prime of a over 2, 2 factorial is just 2. F double prime of 1 over 2 is going to be negative 1/9. X minus 1 squared. And then plus f triple prime over 3 factorial. So that's going to be 8 over 27 times 1 over 6, or that's going to be 4 over 81. So the 27 times 3 makes an 81, and the 2 cancels with one of the 2's on top. X minus 1 cubed. So instead of dealing with a power function with a non-integer power, we can approximate this by dealing with a polynomial, just a cubic. So a linear combination of power functions with positive integer powers. But again, we make an error when we do that. This isn't exactly the same function. This isn't the infinitely long, the full Taylor series. This is truncated. So what does our error look like? Well, what do I need to find? Well, I know that for n equals 3, I have something over 3 plus 1 factorial, or that's 4 factorial, times absolute x minus a to the n plus 1, or absolute x minus 1 to the fourth, And I need to find an upper bound for my n plus first derivative on some interval. So my fourth derivative is negative 56 over 81, x to the minus 10 over 3. I'm really interested in the absolute value of this, right? That is what I want to bound above. So I can get rid of that negative. And I want to find the max of this on what interval? Well, that was on the interval 0.9 to 1.1. So if I say I'm going to be making an estimate in this interval 0.9 to 1.1, I can bound my error. Now, something to kind of note is that obviously the further we get away from the center, the worse our estimate tends to be, the higher this upper bound is going to be, because x minus 1 can be larger and larger the further away we get. But for here, 0.9 to 1.1. I do notice that x to the minus 10 thirds is like 1 over x to a power function. This is decreasing for positive x's. What's decreasing overall for any x except 0, I suppose? This is decreasing, so its max is going to be at the left endpoint. So this m is going to be the fourth derivative at 0.9 in absolute values, or 56 over 28 times 0.9 to the negative 10 over 3. I can put this up here. And then I can say if I'm on 0.9 to 1.1 for x in this interval, absolute x minus 1 is going to be less than 0.1. I'm never more than 0.1 away. So on the interval, my remainder, my error, is going to be less than or equal to 56 over 28 times 4 factorial times 0.9 to the negative 10 over 3. And then absolute x minus 1 is always going to be less than 0.1. So absolute x minus 1 to the fourth is going to be less than 0.1 to the fourth, or that's 10 to the minus 4. Not the nicest number ever, but we can just come over to our calculator. And we can just type this in. So what is it? 56. So 56 over 28. 4 factorial is 24. So that's another over 24. I have a times 0.9 to the power negative 10 over 3. 56 over 28 over 24 times 0.9 to the negative 10 thirds. That looks good. And then over 10 to the fourth, 10,000. And what I got over here. I actually didn't calculate it on my notes. So, but just checking to make sure that everything went in right. That looks right. So I didn't write it out in my notes. So I hope that I typed everything in right. Or that's about 1.18 times 10 to the minus 5. Oh, not down there. I'm telling you, I have like just such a case of brain fog that I don't know what my deal is. Well, I do know what it is. It's allergies driving me crazy. So this is our third partial sum of our Taylor series approximation going up to a cubic term, and our error in making the estimate of and approximating 2/3 or x to the 2/3 by this polynomial, our error will be bounded above by 1.18 times 10 to the minus 5 in absolute values, as long as our inputs stay between 0.9 and 1.1. Any questions on Taylor and Maclaurin series? Okay. I think what I'll do is just post the series review to Blackboard. So it'll just be a list of a bunch of series problems, and I'll also post solutions a little bit later. So you can, use the rest of class time today, because I think if I tried to go through it, I would not do a great job. And we want to be able to get through too much in just about 15 minutes anyway. So I'll post the series review to Blackboard shortly after we're done with class here. And so take a look through that. And then I'll have solutions posted in the next couple of days so that you can review the solutions and see if they're in line with what you came up with it for your solutions. Are there any questions on anything in chapter 11, sequences and series? All right, then next week we will start in the chapter 12, starting kind of the home stretch of the course. And again, unit 3 exam is next week, so make a plan to take that, not at the last minute, take it at least a couple of days in advance, so that if anything goes wrong, you do have a buffer, you have some time to work things out. Otherwise, I will see you all next week for chapter 12. Have a good one.